Okay, so up to this point in the above example, which was example 1 we just completed, both relations and the inverse relation happen to be functions. In such cases, when you have the two relations that are functions, and both functions can be called inverse functions. So you have an original function and your inverse function. So a function is different than the relation in the fact that your functions have to pass the vertical line test. Alright, and we can talk about that in just a little bit. Moving forward, your inverse function, if you have functions f and g that are inverses of each other, you know that when you plug in g of x into your f, just like the composite functions we talked about in lesson 3, you're going to end up with your x value out. Just the same as if you take your f function and plug it into g, you're going to get x out. Alright, we can talk about that a little bit in example 2. When you have an inverse function, we're going to notate that by f to the little -1 of x, which reads as f inverse. So if you have an inverse function, we're going to notate it with f, which looks like the -1 in the exponent spot, x. So that represents your f inverse. Lastly, one good thing to know is if you're given a function, any function, you can always find its inverse relationship by switching x and y. We talked about that before. For a linear function, which means you have your slope and y-intercept, very similar to f of x equals mx plus b, where x is not equal to 0, the inverse of itself is going to be a linear function. Just like I showed you on the previous 3 graphs from the first page, here we have a linear function. If we reflect it over your graph, which has the y equals x line, all your points flop, and you're still left with an inverse relation that is also a function. It's a linear function. So you're going to get lines for both of them. If you start off with a line, your inverse function will also be a line. So let's move on to example 2. In example 2, you're given two functions. Well, you're given an original function and you're told what its inverse is. And they want you to show that these two are in fact inverses of each other. So we can't just take it for what they say. We actually have to prove that this inverse, or the f inverse, is in fact the inverse function of our original. So we start off by taking, well, first I want to replace f of x with your y. So all I'm going to do is I'm going to rewrite my original, where I take f of x out and I plug in my y variable, just because it's easier to solve for y if I have a y. So my original function, or my original equation or function, is y equals -3x plus 6. That's my original. So now what I'm going to do is I'm going to swap my x and y so I can solve for y and find out what my inverse is, and hopefully it matches the one that they're giving me. So if I go through and I rewrite this, or I solve for x, the first thing I'm going to do is I'm going to subtract 6 from both sides. So when I subtract 6 from both sides, I get, trying to hide this from you guys, I get x minus 6 equals 3y, I'm sorry, -3y. I'm going to go through and divide both sides by -3, and when I divide both sides by -3, my -3's cross out. So I'm left with y equals positive 1, y equals, yep, because that cancels out, 1x minus 6 all divided by -3. If I go through and I separate these two, I get y is equal to -1/3 x plus 2. So I can show you that middle step real quick. Y equals -1/3x, and then you would separate this with minus 6 over -3. The double negatives give you the positive, so this is what you end up with for your inverse. And because this matches my original that was given to me, my answer is yes, they are in fact inverses, and you went through the work to show that this, your inverse, your f of -1x, which is your f inverse, is the correct inverse of your original function. Okay, so moving on, finding inverses of nonlinear functions. So these are nonlinear functions, which means we're going to look at an example that has a quadratic. So the graphs of the power functions x squared and x cubed are given below, and I'm going to use some markers here to kind of show the difference between them. So your original is given in your blue marker. to both of these. And again, your inverse function, just like the linear ones we talked about on the first page, still reflect over your y equals x line, which is that 45-degree line, which results in the following graph, which is the orange one. If your domain of f of x equals x squared is restricted, say, to the only non-negative real numbers, then the inverse of f is a function. So in this case, what does that really mean? We kind of have to restrict our functions, our inverse functions, so that we actually get a function out of it. So if I take, for example, if I take my original blue quadratic and I flip it over my y equals x line, I end up with this orange quadratic, which I know does not pass my vertical line test. So this orange function, the way that it's graphed right now, does not pass my vertical line test, so I know that this orange graph is not a function unless I restrict it. So restricting it means I have to actually cut off part of that graph in order for it to be a function. Now over on the right, my cubic function, in this case, if I take my blue function, or my blue graph, and I flip it over my y equals x line, which is the pink one, I'm going to result in this orange graph, which does pass my vertical line test.